Our next topic is thermodynamics. Thermodynamics is a study of heat energy and its relationship to other form of energy. It's a field that explains everything from, for example, why your coffee gets cold to how a car engine works. And in order to understand thermodynamics, first we have to understand some basic terminologies used in the study of thermodynamics. Uh, uh, the very first step, whenever we are analyzing a thermodynamic problem, the first step is to define our system. The system is the specific object or reason that we are interested in studying. So basically, this is area of interest, a region of interest. For example, if we are studying a cup of coffee, the cup and the coffee inside it will be our system, and everything else in the universe, the room, the air, the table, is considered surrounding, and the line that separates this system and surrounding is called boundary. On top of that, we also need to understand what is internal energy. We talked about internal energy in our previous section, and we defined the internal energy as the sum of all the potential energy and the kinetic energy of all these tiny particles within the system. And since it's the sum of kinetic and potential energy, if we add more, if we add heat energy in the system, it will increase the kinetic energy of tiny particles, resulting in increase in internal energy. Heat at internal energy increase. And if we remove heat from the system, then it results in decrease in internal energy, because if we remove energy, it will decrease the kinetic energy of the moving particles. And here we can see example of energy conversion from one form to another form. Energy conversion happens all around us. A simple example is friction, which converts mechanical energy directly into heat energy. We can look at an example of rubbing our hands together on a cold day, and you basically, when you are rubbing your hand, you are converting the mechanical energy of your hand movement into heat energy. And we can see a more complicated example in this animation. The person on the bicycle is providing mechanical energy by pedaling the bicycle, and that movement is transferred to the generator. And when the generator is rotated, the generator converts the mechanical energy into electrical energy, when which then powers the light bulb. Here, the electrical energy from the generator is used to power this light bulb, and this electric energy from the generator is converted into heat energy to increase the temperature. Increase the temperature of this filament. And once it reaches certain temperature, it will emit some light as a and it will emit some light, and that's why it's called light bulb, and it is the byproduct of heating this filament. So basically, mechanical energy converted into electrical energy, and electrical energy converted into thermal energy. And the first law, there are few different laws of thermodynamics, and the first law of thermodynamics is the conservation of energy. Uh, the, Basically, the first law of thermodynamics is a restatement of uh, the conservation of energy, and it tells us that energy cannot be created or destroyed. It can only be transformed from one form to another form. That's why the first law of thermodynamics is often abbreviated as you can't win. Is associated with this term, you can't win. Basically, it means that you cannot create energy out of nothing to get ahead. So you should use whatever energy is already there. And mathematically, this first law of thermodynamics is represented by this formula, where Q is the heat energy, W is the work, U2 is the final internal energy of the systems, and U1 is the initial internal energy. And then the calculation of internal energy is a really complicated process. So whenever we are solving problems in thermodynamics, we generally do not calculate internal energy, uh, but we are mostly interested in change in internal energy. So even though we will not calculate the internal energy at equilibrium state, we are mostly interested in change in internal energy from one state to other state. For example, we have a system here, and the internal energy in this state is U1. Then in the system we added some energy, and say this is our new system. After we added the heat energy, then this system will have some different internal energy, and the change in internal energy from this stage to this stage is defined as delta U. And the energy heat energy we added is represented by Q. And whenever the system changes from this state to this state, for example here in this example we can see there is some volume change from this volume to that volume. That means it's doing some mechanical work here, so we can say that is work on the system. And this work can be on the system or by the system. For example, here this we added energy, and the volume is increased. That means the work is done by the system. And if we were to apply some external force to do some work on the system, then that will be work done on the system. So work could be positive, negative, based on whether the work is done on the system or by the system. In summary, the first law of thermodynamics is defined by this equation, where the internal energy is equals to heat energy minus work done. And we can see an example here. We have a heat engine here, four stroke heat engine. First, we can see here there are four stages. In the first stage, the heat engine uh, sucks some years, and then air plus fuel mixture it sucks in the stage 1, it sucks some air and fuel mixture, and then the piston in step 2, the piston moves up, compressing this air fuel mixture and increasing the internal energy, because we have done some work on the air fuel mixture, uh, compressing it from this size to only this size. And once it's compressed in the stage 3, there's a spark plug here. It will create a spark, uh, 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 it will create some spark. And since the internal energy of this air and fuel mixture is very high because of the compression, and on top of that there's a spark here, then suddenly all the fuel will burn using the oxygen in the air, resulting in rapid change in energy. We gain high thermal energy by burning the fuel, and once the energy is very high, it will push this piston down in the step 3, resulting in this constant rotational motion. And once it's burned completely, piston will move up, and it will exhaust the burn fuel as the smoke we see in our car. So basically, the chemical energy of this air fuel mixture is converted into thermal energy by igniting it, and the thermal energy of this air fuel mixture, the thermal energy generated by burning air fuel mixture is converted into rotational energy by moving this piston up and down, and ultimately moving this crankshaft in a rotational motion, resulting in mechanical energy. We can also see this is an animation. It should be working. This is not working. So basically we have this two different particles here. As we increase the temperature, it will also increase the pressure and internal energy, because we are adding heat, meaning resulting in increase in temperature. And once it reaches certain temperature and pressure, because of increase in kinetic energy of this motion, it will apply, it can, the air mixture is able to open this lid. So basically showing the thermal energy resulting in mechanical energy. And the second law of thermodynamics is often summarized as you can't break even. This law has three equivalent statements. The first one is no process can convert all heat into work. Uh, that's where this statement "you can't break even" comes from, meaning you cannot have a system that is capable of converting all the work provided in the system, all the heat energy supplied to the systems to works. Yes, basically efficiency cannot be 100%, it will always be uh, less than 100%. So this sign is called is a Greek letter eta, generally used to denote the efficiency. And the first statement of second law of thermodynamics states that no process can convert all heat energy into work, uh, and some input energy in the system will always be lost in surroundings. And the second statement is Heat never flows spontaneously from a cold object to an hot object. It will always flow from uh, hot object to cold object, meaning the natural direction of heat energy flow is from hot body to cold body. And here spontaneous means without any external help or without any external work. So naturally, if we have two systems, one system is we can see it in here in image. We have two systems, and one is hot, one is cold, and if and the heat energy is transformed from this hot body to cold body, and at if they are constantly in contact, at some point they will reach the same temperature and the heat transfer will stop, and that point is called equilibrium condition. And mathematically this second statement can be represented as uh, q hot is equals to work done plus q low, meaning there will be some work done uh, whenever we are changing the temperature of this low heat system or low cold system. There will be also result that will also result in external work done. So the total heat energy in hot body is equals to work done plus uh, heat energy in the low temperature system. And the third statement is the natural processes tend toward a greater state of disorder. And the disorder, when we say disorder, uh, basically what we are saying is the in nature all the systems try to always move towards higher order of greater state of disorder. For example, if you have for example we have an egg here, right, and if we break it, then it's spilled here. So what this is trying to say is that when if you break this egg, it will easily get it will easily get into a greater state of disorder. It's spilled here like this, and naturally this will never get in this like the original position of low disorder. For so that's basically the statement is saying the natural way of things is that all natural processes will tend toward a greater state of disorder. For example, one more example, we have a glass cup, and if we break it, it will be the shards of glass, and naturally it will not come from this state to this state because this is high entropy, high disorder, and the measure of this disorder is called entropy. And this is when the cup is not broken, and this is a lower disorder compared to the other fits. So in summary, uh, second law of thermodynamics has three equivalent statements. The first one says no thermodynamic system will have an efficiency of 100%, there will always be some energy loss into the surroundings. And the second statement is naturally the heat always flows from a hot body to cold body, and the total heat energy in the hot body is equals to the work done plus the heat energy in the heat energy in the cold body. And the third statement is there's that in the natural processes always tend toward a greater state of disorder. And uh, and we can also define it we also defined it with a different example. uh, for example, one more thermodynamic. Let's look at one more thermodynamic example. uh, if we have ice, say we have ice block, and naturally if we leave it in a natural conditions, it will melt and form a liquid. And as we looked at this example before, and we said the kinetic energy of this particle is lower in the solid is lower compared to the liquid, meaning the disorder of this particle is higher in liquid. uh, and the nature and we also know that naturally the liquid will never change into a ice block until and unless we do some work to convert the liquid into ice phase.